Hello, in this talk, I will demonstrate the various ways the microcontroller kit can be used to upload code to a microcontroller to acquire data from a color sensor. The sensor is connected to the microcontroller using an I2C interface, and the microcontroller is connected to my laptop using a serial interface. Welcome to my talk. I'm Suba Thomas. I'm the developer of the microcontroller kit. My objective in this talk is twofold. First, naturally, I want to demo the sensor, but secondly, I also want to go over I2C communication using the microcontroller kit. I've given quite a few talks on the microcontroller kit, but I2C communication is something it's a little bit more involved, and it's not as straightforward as, say, blinking an LED or getting an analog input. So in this talk, I want to focus a little bit more on I2C communication as well. Okay, first let's look at the sensor and also at I2C communication. This is the image of that sensor module. The actual sensor itself is that component right there in the middle. So how does this sensor work? So it has this array of photodiodes. Some of them are clear, some of them are red filtered, some of them are blue filtered, and some of them are green filtered. So the current that flows through these diodes is proportional to what it's sensing. And for a preset amount of time, these currents are integrated. And the value we get is a measure of how much of that particular color the sensor is seeing. Now, as far as I2C, is it too small or is it okay? It's okay. So I2C stands for inter-integrated circuit, or it's also called TWI, or two-wire interface. So in this protocol, communication happens along two wires. One is the SCL, or the serial clock line, and the other one is SDA, or the serial data line. And there is one master device, and the rest are all slave devices. The master is responsible for generating the clock signal, and all the slave devices are synchronized to that one master to that clock signal. So it's a serial synchronous communication protocol. Now, each slave in this configuration has a unique address, a 7-bit address. So in one setup, you can have up to 2 to the power 7 or 128 slave devices. And each slave is so the master is the one that initiates any communication, whether it's reading or writing to any of the slaves. And the master does that by sending first a start signal and then giving the slave address on the data line. And then it gives a read or write, okay, 1-bit read or write to let the slave know whether it's going to read or write from that particular slave. So in I2C, there are 7 this kind of specifications. There is the start, there is the stop, there is the write to slave, there is the read from slave, there is an acknowledgement bit, there is a non-acknowledgement bit, and then the rest are all data bytes. So the data is like the address of a register, the value to read from a register, and the value to write to a register, and so on. So the physical setup I have here is so I have this sensor here. So there are only 2 wires again. So the black and red are just the power lines, and then the SCL pin I connect to the SCL pin on the Arduino, and the SDA this is the SCL, and the other one is the SDA, and this one I connect to my laptop. Okay. So there are several ways we can go about doing this. So one of the ways is to use this sensor I bought from actually Adafruit sent it to us. So we can use the library that they provide, or we can go a little more low level and use just the wire library that comes with the Arduino IDE, or we can just start from bottom up. So we can compare these 3 approaches, and because these are 3 parallel approaches, there's going to be some overlap in the code. And so I have this functionality that I'm just going to reuse in each case. So the first thing I do, of course, is to load this package. And over here, I just have this one Arduino connected to my Mac, and I can identify the port name by looking at file names of this form. So then I create a utility to create a file. So what I'm going to do is, in each approach, I'm going to log my inputs into this file. And so at the end, the size of this file is going to tell me how involved my effort was in each approach. And then this is the utility to append the output. It's basically put append to that file. And then I get to the actual communication itself. So the data that's coming back over serial comes back as a start byte, a delimiter byte, a start byte, then the actual data, a delimiter byte, and an end byte. So it's best explained using actual values. So I've just simulated the kind of readings that are going to come from the sensor. So if you have the 3 values, what's going to come back from the sensor is this kind of ASCII codes. And so what parse data does is basically reassemble those values. And then I create a pie chart. So I can do. So it just gives a pie chart of. And then I have this other visualization utility okay, so what it does is, if a stream of data has come in, it plots the different red, green, and blue levels, and also that pie chart above. The pie chart of the last data point. And then this is the utility to open and read from the Arduino itself. So I first open a connection to the device. So after I upload the code, the Arduino is basically like a serial device. So I open a connection to the device, and then I create a scheduled task, which, if there is data, it gets that data, it reads that data, parses it, and if it's okay, it appends it to this list, RGB list. And then I flush the buffer so there's nothing stray left there. And then finally, this is an utility to remove the task and close the device. Okay, so let's move to our first approach now. So I create this file, and now after I evaluate this, all the input I evaluate after that is going to be logged into that file. So I set a sampling period of 0.05. This is like a design parameter. This worked fine in my case. And then this is the core computation that's going to be running on the Arduino itself. So if the clear signal is less than this 3500, you get it by trial and error, basically the sensor is not seeing anything. And so I set all the channels as 0. Basically it's black. And if it's not, then I normalize it using the clear signal value. Now I'm going to use the library, so I have to specify the library path, and these are the header files that I'm going to use. And this is the data object in that library for that sensor. And then I go about initializing that sensor. So when I deploy this code and it's actually running on the Arduino, when I begin, it's going to establish a communication through that I2C interface with the sensor. And this is the function to get the raw values. It gets the raw red, green, blue, and clear values. And then this is how I specify my input channels. So in each case, it gets it through the external library code, and each one, so the first one returns clear, the second one returns the red, green, and blue. And the output from the Arduino is the serial output. So this, once I have that, this is going to give me the complete microcontroller specification, the target name, the files I include, the utilities, the initializations, the input and output channels. And at this point, I'm going to upload the code. So you should see the Arduino. I cannot see it like that. Okay. So here also it gives me an indication that it's both generated the source code and uploaded it to target. Yeah. Okay. So now I stop logging into that file. I now open, and so at this point the Arduino started reading from that sensor, and now I open and read open a connection to that Arduino and start reading. Okay, so we can use any program. I'm using again the Wolfram language, the device framework in the Wolfram language. And now I start, let's see what it's seeing. Okay, it's basically not seeing anything. So I'm going to take one of these mini breadboards. It's a, you can also see it up there. So you can see what the individual diodes are picking up and the net color. So we can try with different colors. Yeah. And then if I give a white, it should, all the channels should pick it up. Okay. I cannot. Okay, so this was one approach. Now I'm going to stop that task and close the connection to the Arduino. Okay, so now let's look at the second approach. So in the first approach, when we used the library, a lot of the internals were shielded from us. So now we have to go a little deep into both the sensor and also the I2C specification. So this is the state machine for the sensor. So there is a bit called power on. When you turn it on, it goes into this state. I'm not going to wait. This is useful if you want to conserve power and the sensor is running off a battery. But I'm not going to do this. I'm just going to go from this state to enable. And then it needs about 2.4 milliseconds to initialize. And this is the integration time that I can set. So if we set a high integration time, a greater value will be returned. So that's again a design parameter. So what I'm going to do is go into the idle state and then get into initialization and obtain the data and keep looping like that. Okay. Okay. So this is just like before. I create this file. Now I start adding to that file. This is the same as before. And now I'm going to set a preset integration time. In the last case, I used 50 milliseconds. So here also I'm going to use 50 milliseconds, but here I directly have to write to the register on that sensor. So this formula here, it comes from the data sheet on the, not this, yeah. So this is that register itself, and when I put in a particular value into this register, this is what the integration time is going to be. So in the data sheet, it will tell you how to calculate these values. So if you want a particular integration time, what value you should store in that register, and this is the formula I've used here. I'm using the same integration as 50 milliseconds as before, and that should be the value. And then all these, which I use in uppercase, are the I2C address of that slave device, the register address, and so on. So again, all these look like magic numbers, but they are all in the data sheet. Yeah, I'm using this enable register. I'm using this 8-time register, the control register, and this are the registers in which all those values for the clear signal and the red and the green are stored. So these are all the registers I'm going to use, and that's what I've just copied from the data sheet onto here. Okay. Yeah, so I have the enable register address, and these are the bits, the bit locations where I'm going to enable it. This is the timer register, and this is the value. This is the register where I set the gain to be 4 times, and this is the this is the register where the clear data is starting, the low bit, and I don't have to, because they're all contiguous registers, I just start with the first and it just goes to the next 8 ones. So this is the incantation to write data. I start, and then I give this command code, the register value, and write what I want to do in that register. So when I initialize, this I'm going to use when I initialize. So when I initialize it, in the timer register, I'm going to set how much time I want to integrate, how much gain it should be, and then I enable the sensor and then stop it. And then in a loop, I again start, I give the address of the clear data low byte register, and then I read 7 of them, and each time I read, I acknowledge, the master will acknowledge that it has received, and then the final read, and then I stop. Okay, so this is the I2C specification. So at this point when it is running, it's going to get these 8 bytes. So but we need to know what to do with these 8 bytes, and that's why I created these functions. So for the clear function, so the first data bytes that are coming in are for the clear function, and so the first is the low byte, and then I shift the high byte, and I do that for all the other inputs as well. So then that will give me the complete input channel specification. Everything is the same except for the conversion function. So all these inputs get it from the slave device, and this is the conversion. And as far as the output of the microcontroller, it's a serial output. So this is the same as before, the microcontroller embed code, the core system I want to upload, the same target, and these are my input and output specifications. It should. Yeah, it's finished uploading, so I stop logging the data, and as before I start. Okay, this time I can use something else. So you begin to see the local line. So it's the same as before, just equivalent code. So yeah, and finally we are going to not use the wire library also. We are just going to get the microcontroller kit to just generate code from the bottom up. So just as before, I create that file. Now I'm going to input, and the core code is just the same as before. So I just have it as an icon there. So the only difference between this and the previous one is that over here I did not use, I used the wire library. Okay, and over here I am not. That's the only difference. And just to make sure we can go through the same process again, I have a green breadboard. It should see the green color. And so let me. Okay. So now that I've gone through these 3 approaches, I wanted to see what the file sizes are. So there are 3 files. So one is the Wolfram language code itself. The other one is the source code that was generated by microcontroller embed code, and finally is the machine code that was deployed onto the microcontroller. So you see, so if I'm using the library, I have very little code to write up front, but then the machine code that gets deployed is large. And if I'm using just everything from the bottom up, I can get a really low code footprint on the microcontroller. Just as more pain and more gain. Okay. So this is an application. Yeah. So there are people do several things with this color sensor. So this is something it came up quite naturally to me. So when I was working with the microcontroller kit, typically I'm looking at LEDs, and sometimes if I just look at them for too long, it strains my eyes and things begin to appear blurred. So I realized that I could use this color sensor with chromaticity plot to see what colors I was outputting, and then see if it was doing the necessary thing. So I already have the code running there, and just like before, I'm going to read the data and parse it. Okay. Yeah. So before I do that, I have this. Where did I put it? Yeah. So I have this Adafruit Flora, and there's a code running on it, which sends a range of colors to this NeoPixel. So let me plug this in. I should bring it here so you can see it clearly. So you can see that it has it's just cycling through a lot of colors. It's a little hard to see over there. Okay, so now I can and then I'm going to hold this on top of this, and hopefully it should pick up those colors. So I know that that's the code that is running on that other microcontroller. I know that it's cycling through those colors. Okay, so to summarize my talk, so in this presentation, I used this TCS 34725 sensor to get the color and sent it and programmed the Arduino Uno to get the color values from that sensor and send it over serial back so that we can read it using the device framework. So the main function I used was, there's only this one function in that packlet. It's microcontroller embed code. So it will do all the underlying work for you. It automates that whole process. It will go through generating the source code, compiling it, and uploading it to the microcontroller. So there is the documentation for that, and also there is documentation for I2C itself. If you want to set more options and so on, there's more documentation there. And of course, I use the Wolfram language for the rest of the tasks, especially the device framework and visualization and the dynamic interactivity and other miscellaneous stuff. Right, so I think that concludes my talk. Thank you. Yeah, the sensor? Yeah, so that's, they say that upfront. So let me go back. See, so once we give a request, it takes about 2.4 milliseconds to initialize. And then we can set how much time we want it to keep measuring it. So all that time it's going to keep adding the current. So we can go up to 614 milliseconds. So just to do one measurement, we need about 616 milliseconds. But the sampling period I set is 0.05, right? So it's much higher than that. Yeah.
So three approaches you took. Other than the size of the code being deployed, is there anything else that's different?
Yes, it's just the different effort. Eventually, it's the same code. It's equal.
Performance and everything will be similar on the microcontroller.
Yeah.
Once it's deployed.
Yeah. It's different ways to get to those registers on the microcontroller, different mechanisms.
And space is an important
Yeah.
area for these.
Yeah. So if you look at this, see when it comes down here, it's about 4 kilobytes. Yeah, and then there are microcontrollers which have 8 kilobytes, 4 kilobytes. So if you want to squeeze it into one of those, you can squeeze it into a much smaller target. Yeah.
So the second method and the third method, the difference is the language?
Yeah, language. So one uses, one is, it uses the wiring library that comes along with the Arduino IDE. And the other case, the microcontroller kit is directly writing to the registers. So the other one, another library called the wiring library is writing to the registers. Here it's the final approach is really bare metal. If you look at if you look at this, can you see that? Okay. So you'll see all these registers. Okay, so this is start. So it's going there to that register and setting those bits. It's very low level. So you need that kind of fine grain if you want to really make the size compact.
And you got that out, that information, where did you?
I just get asked for the source code. And you can just copy this, put it into the Arduino IDE and compile it from there, and that will work too.
I came in late. Can you put in source code, inject it into the Arduino through that interface?
Say that again?
Can you inject the source code you're showing here?
Mm-hmm.
Is that something I can inject into the Arduino from a Wolfram front end?
So under the hood, it generates the source code and deploys it. That is hidden from you. But you can extract the source code like this and copy paste over to the Arduino IDE, and then inject and then go that route. So the other thing that we missed is if you have the source code, to give that to microcontroller embedded to embed it. That we have not done yet.
I think the whole kit is doing what you're trying to say. The whole kit does it. So if I wanted to put some of my own code, because I recognize, I program those things, I recognize that setting certain registers and machine stuff. And if I want to do it,
If you want to write your own source code, if you want to write you can start from the Wolfram language. So here, when I'm using the library, I'm actually mixing. Over here, when I'm using the library, I'm actually mixing code. I'm saying which header files to use and so on. So when you're working with the library, you're working with both the source code and also leveraging something off the microcontroller kit. But the final approach is completely from the Wolfram language. And this one is just an interaction between the two. Okay. All right. Questions? All right. Thank you then.